Okay, let's see one more example to prove by mathematical induction, which is given in the book. It's for sum of the geometric progression. So what we are interested to find is to prove that the sum of geometric progression formula is true, right? So that we need to prove. So let's see what does this means and how it is going to be proved. So it says the sum of geometric progression j starts with 0 to the n, which is a r to the power of j. Prove it, right? This is nothing but it is actually going to be when j is going to start from 0 to n. That means a r power 0, which is a, plus a r power 1, which is next is a r square, next would be a r cube, plus so on, plus a r power n is going to be equivalent to the a r power n plus 1 minus a divided by r minus 1. And this should be true for all. It should be true when r is not equal to 1. Obviously, if r is equal to 1, it's going to be 0. Denominator will become 0, which is infinite, which is undefined. And this is true for all non-negative integers. That means n should be greater than or equal to 0. So all non-negative integers, this is true. So we are asked to prove it by mathematical induction. So we can do that. Let's see, we already have seen few examples in our last video. So my step number one would be, step number one is going to be, let P of n is going to be a plus ar plus ar square plus ar cube plus so on plus ar n is equal to a r n plus 1 minus a divided by r minus 1. That's what we have assumed now. Okay, then I am going to do the step number 2, which is my basis step, right? So we have to prove it for the smallest value of n. So since the smallest value of n is going to be 0, so we have to use n is equal to 0 here for the basis step. Now, what does this mean? I'm going to find it for P of 0, which is here is A. The first term is A. When n is equal to 0, it is going to be A only, is equal to, on the right-hand side, I'm going to substitute n value as 0, which is going to be A r to the power of 0 plus 1 minus A. So let me just make it clear. R 0 plus 1 minus A divided by r minus 1, which is going to happen now. This is equal to ar minus a divided by r minus 1. So we have to make it equivalent to the a. So what we can do here is we can, on the numerator, I'm going to take a as a common, which is now going to be r minus 1. So right from this term, I have chosen r as a as a common. From here, I have taken a as a common. So the remaining term is only r minus 1 divided by r minus 1. And then r minus 1 and r minus 1 should be cancelled out, which is going to be a. So we have proved that we have shown that the basis step is true, which is correct. So which is true, right? The basis step is true. This holds for n is equal to 2. Now the next step is my step number 3, right, which is the inductive step, which is inductive to set up the induction hypothesis. So what is my induction hypothesis? Induction hypothesis means I have to show that it is true for any arbitrary value, any arbitrary term, which is k. So what I can do is I can set up the kth term. How can I do that? I'm going to say P of k is going to be now a plus ar plus ar square plus ar cube plus so on plus ar k. Instead of n, we are going to substitute k, plus or equal to ar k plus 1 minus a divided by r minus 1. Right? So that is what my induction hypothesis is. Then what I have to do is, then I have to prove for n is equal to k plus 1, right? That is what I have to prove. So let's add this now, do this for k plus 1 value. So that is going to be now, which is going to be a plus ar plus ar square plus ar cube plus so on plus ar power k. The next term would be ar k plus 1 term, right? So let me just make it clear. Ar k plus 1 term is going to be equal to, instead of k, I'm going to substitute k plus 1 on the right hand side, which is ar. Instead of k, I'm going to substitute k plus 1 minus a divided by r minus 1. Right? So that's what I am going to solve now, that I have to show. So we already know here that the value of this whole term is here, which is this one. So I will use this value to solve this one. So now I'm going to use this value, which is a r to the power of k plus 1 minus a divided by r minus 1 plus the remaining term, which is this one, a r k plus 1 is equal to a r k plus 1 is k plus 2, right, minus a divided by r minus 1. So that's what I have to prove. That's what I have to show. So now it becomes simple. I can just simply show that for this term, I can multiply it with r minus 1 and divide it r minus 1, so that I can write these whole terms in the combined format. Right? So that's what I'm going to do now. So I'm going to write it like this one: a r to the power of k plus 1 minus a plus r minus 1 times a r to the power of k plus 1 divided by r minus 1. Right? That makes a perfect sense. So now then on the right hand side, what we have is equal to a r to the power of k plus 2 minus a divided by r minus 1. Okay, now what we can do here, let's multiply this r minus 1 with a and with r also, the next both terms. So how we can multiply them? Let's see. A r to the power of k plus 1 minus a plus, when I multiply it with r, it is going to be a r. So since the base are same, the exponents will be added, which is r k plus 2 will become a k plus 2 minus minus 1 with this whole term, which is going to be a r to the power of k plus 1, right, divided by r minus 1. And on the right hand side, we have the same value, nothing changed, k plus 2 minus a divided by r minus 1. Okay, now we can now simplify this one. This value is, you can see this value is a positive ar k plus 1, and this value is negative ar k plus 1. So we can cancel them out. This and okay, this is cancelled out, right? So the remaining stuff that we have now is, let me just write the positive value first. From this equation, I'm going to rearrange. This is a positive value, this is a negative value. I'm going to rearrange them to write it like a r to the power of k plus 2 minus a divided by r minus 1, which is exactly equivalent to the right hand side, which is a r to the power of k plus 2 minus a divided by r minus 1. So hence we have proved using the mathematical induction that this formula is correct and this claim is correct. This claim is correct, right? That we have proved using the mathematical induction that the sum of the geometric progression is correct. All right.